It's July 7th. I made the claim at the end that theorems like this are important, even though they don't seem like they're helpful, because they just show you the existence of something, right? And so again, I may offer some extra credit here. Let's see here. So we can show that, let's say, x to the fifth minus 5x plus 3 crosses the x-axis, or I should say the graph of this crosses the x-axis somewhere on the interval, let's say 1 to 10. The fundamental theorem of algebra says that this function crosses at most how many times? 5 times. Oh my God, I love intelligent people. That's right. So 5 times, because the degree of this polynomial is 5. That's the fundamental theorem of algebra. But it may only cross a certain number of times. What's the minimum number of times this has to cross the x-axis? What's the minimum number of times? 1. Is it 1? 1. Okay. So the claim is that that's 1. So the claim is that it crosses at least once. Could it not cross 0? Why can't it cross 0 times? Does this have to hit so this one has to hit the x-axis, right? Because that's what we're about to prove. But I'm going to give you a general question in just a moment. But let's show that this crosses somewhere between 1 and 10. Go ahead.
We can show that it crosses between 1 and 10 by plugging in 1.
F of 1 is 1 to the fifth minus 5 times 1 plus 3. That is
-1.
-1. Go ahead.
So because we know that's negative, we know that's below the x-axis, right?
So this function, whatever it is, starts off below the x-axis. Go ahead.
And then we can plug in 10.
F of 10, I'm not so interested in the exact value, but f of 10 is 10 to the fifth minus 47. I don't really care what that is, but I know that it's positive.
And that's all we need to know.
Because
we know there has to be 0 between those two numbers.
Because
it's a continuous function. To get from that point, from x equals 1 to x equals 10, it has to go through the x-axis.
by what's the reason? By the intermediate value theorem. Thank you. Appreciate it. So good. So that conversation that we just had, it's a conversation that everybody needs to go to, right? And everybody knows that, right? But again, in terms of the level we want to get you at, that entire conversation, you just need to say exactly what you said, and I don't need to say anything, right? So f is continuous because f is what is f? F is a polynomial, right? And so that means that when you graph any polynomial your whole life, you've graphed polynomials of all different degrees, and you never saw one jump, break, or anything, right? You can draw every polynomial without taking your pencil off the paper, right? Every polynomial is continuous. So f is a polynomial, therefore f is continuous on the interval 1 to 10, and therefore, by the intermediate value theorem, f has to take every value between the minimum and the maximum. Now, we don't know whether these are the minimum or the maximum, but we know that f has to take every value between f of 1 and f of 10. Okay, and that's by the intermediate value theorem. That is excellent, right? So next time as we continue to have these conversations, I need to say less and less, and you just need to fill in all the blanks, right? And this is precisely why, it may seem like I'm haphazardly doing things, but I brought this up, and I introduced the intermediate value theorem for us to use it, right? And this is one of the uses. Okay, that is excellent. So yeah, I may throw a question on here like that if you want me, or if I may want you to show that a function crosses the x-axis. Of course, I could say this in all sorts of different ways. I could rephrase this by saying, show f has a root on the interval 1 to 10. Please.
So based on that information as a one, how did you find out what the zero was?
Oh, you don't? I don't know. We just know it's there. We know it's there. Yeah. And so what happens is, particularly for this one, I mean, obviously you could set this equal to 0 and solve. But I purposely made this the fifth root because that's the last degree that actually has a formula. And that formula is ridiculous, right? And so nobody really wants to use that formula, right? But if I put a 7 there, the argument still works, right? And therefore, we know that it's there. And so we have a whole section of mathematicians called numerical analysts who then go about the business of finding what that number is to however many decimal points that my physicist brothers care about, right? They went into 4 decimal places, 5 decimal places. And so one of the ancient ways of finding this place is the bisection method, right? So the bisection method will say, okay, well, I know that the answer is between 1 and 10. And so what you do is you pick some other point, like 5, in this case, maybe 5.5, right? So I knew that it's negative here and it's positive here, and I need to plug in 5.5, and I would see if I plug in 5.5, the answer is what? What do you think it's going to be if I plug in 5.5 instead of 10? That's probably going to be positive. So now I know the answer is between what and what? Between 1 and 5.5. And then I pick another value, maybe 3. Right? And so when I plug in 3, it's looking like still 3 to the 5th is a lot, right?
Yeah.
So it's between 1 and 3. And then I just keep doing that. And oh my goodness, how tedious this is. Right? But of course, this is what we used to do back in the day when we didn't have software and all of these things, right? So this is clearly what a numerical analyst would do. Just zoom in on it. And you can see why they call it the bisection method, because you take the interval and you just keep cutting it in half, right? And so you can also see that this is also almost like a limit process. And so what numerical analysts care about is they care about the time it takes for a method to converge, right? So that if I wanted this within 3 decimal places, how long would it take that programmer using this method to get to the answer? And all they do is fight about trying to write the quickest program, right? And so this is one of the slowest ways of getting to the answer, because you might imagine that you would write code and have to check. You would have to pick a value, check the answer, decide whether this number is positive or negative. If it's positive, then take that number plus that number, divide by 2, plug in that. That takes forever. Right? So there are other ways of finding the roots other than this slow method. Okay. So the answer to your question is that the theorem says there is a value, right? So let's write out the conclusion, right? So by the intermediate value theorem, there is a C between A and B. In this case, it's 0 and 10. I'm sorry, it's 1 and 10, such that f of C is equal to 0. And who knows what it is, but now we've made a pretty good argument that it's between 1 and 2. Yes?
On a test, can you write IVT?
Yes. Yeah. I am not, I try not to be hypocritical. If I write IVT, you can write it. Yeah, so yeah, it would be crazy if I wrote IVT and then you wrote it and you'd be like, and I would say, wait, what are you doing? Yeah, that's crazy. Okay. I want to do a couple of things today. I wanted to do some algebra on limits, and then I wanted to introduce the derivative. I'll take any questions about the intermediate value theorem. So, I don't know what question number we're on. Maybe number 5. I would ask you to use the immediate. I wouldn't even say use the immediate value theorem. I would just say show that this function has a root between these two values, something like that. Questions about that? I'm also, I think I mentioned this during the study time, that I'm concerned about giving a test on all of Chapter 2. Chapter 2 is expansive. I think I might want to break it up into 2 tests. So to have one test that covers all of what you see in Chapter 2, I think is a lot. It's certainly a lot to do in an hour and a half. So, I mean, because that would mean that I would have to create a test that that I would struggle for it not to be unfair. I mean, for as expensive as I want it to be, right? So we're probably going to have 2 tests on Chapter 2. Okay, so we'll go halfway, and then, but I'll let you know, and we'll review and everything like that. But I wanted to let you know that. Okay, there was an earlier question. Show that any odd degree polynomial on the real line crosses the x-axis. So we had x to the 5th minus blah, blah, blah. We were pretty certain that crossed the x-axis. I gave you the interval. It was 1 to 10. I'm not going to give you an interval. I'll just say that if you give me x to the 7th minus whatever, if you gave me x to the 131st plus 4x plus 3, any odd degree polynomial has to cross the x-axis. Why is that?
It's because at the opposite end state, the y tends to different directions, so it eventually has to cross the x-axis at some point.
Because
you need like your
I need an interval.
From negative infinity to infinity.
Oh, that's not an a and a b. A and b have to be real, and you have to include them. So you're almost there. So you're talking about in behavior, right?
Yes, sir.
So at one end, so the in behavior on opposite ends is opposite, but the in behavior on opposite sides of the real line is opposite. So there's a place where it's
Positive.
Let's call that place A, and there's another place where it's, if you want to call it, and on that interval, f is, and therefore by the f has to
Cross the x-axis.
That's correct. Excellent. Perfect, right? So an odd degree polynomial, right? It has the in behavior. And so this is a pre-calculus. Is opposite on the real line. What is glorious about you all, amongst the many, many things I could go on for days about how glorious you all are, but you all from all sorts of different places. So I don't know whether you all talked about rising to the left, falling to the right for polynomials. We talked about that. So when you have something of odd behavior on the ends, it's either coming down from here and doing whatever it does here, and then it has to do that, or right, it has to come down from here, do whatever it wants to do in the middle, and fall. So every odd degree polynomial has to do that. And the argument for that is not that difficult, right? X to the 7th minus 4x to the 4th plus 2, for example, I know that this rises to the right and falls to the left. How do I know that? Well, I'm asking really about the limit as x goes to infinity. And as x goes to infinity, oh my goodness, x to the 7th just annihilates this stuff. I mean, if 4x to the 4th wants to join this fight and say, yo, I'm negative 4x to the 4th, You may be getting big, but I'm getting really negative, right? The fact that the degree is odd. What does degree mean of a polynomial? It's the highest power, right? And so because the degree in this case is odd and 7 is the highest power, then it gets way more positive than 4x to the fourth could ever get negative, right? That's the point. And that if this is over here, minus x to the ninth plus whatever, right? 7x to the eighth even, right? Early on, this might seem like it's bigger, but as you get higher and higher, x to the ninth will get so positive, way more positive than this, so that when you put a minus sign in front of it, the whole thing becomes eventually negative, right? And that's all on the right-hand side. On the left-hand side, of course, we're making x really, really negative. So if I made x go to minus infinity, we are now going to use the fact that this is odd, because I know that a negative number to an odd power stays very negative. And that's why this has to fall to the left, right? Now, according to his argument, for this particular case, if it is the case that I know that this is going to fall to the left, there is an a such that f at a is negative. And similarly on this side, there's a b where f of b is positive, and this game is over, right? Because then that's the interval that we need. F is a polynomial, it's continuous. We can then clearly invoke the intermediate value theorem, and we have exactly what we need. So that's the type of argument. So that type of question for sure is like a bonus question I would put on a test, right? It fully tests whether you understand a ton of different things, right? So, but it's extra credit because, again, you know, if it's not, that wouldn't be something that I would have fully talked about in class. So I would not feel fully okay with testing it. That's a philosophical perspective in terms of teaching. Some teachers just love, you physics people, wait till you see some of the tests you get, like of stuff that you never talked about. That's just a different philosophy, right? So, yeah. Okay, anyway, questions about this and that reasoning? Okay. Let's do some algebra of limits. The limit as x tends to 3 of 5x plus 1. And I forgot, one of you two talked about plugging the number in, right? I think it was over here. We talked about doing one of these limits and just plugging the number in. Here's a theorem. Every polynomial is continuous. I had said that on the whole real line. This is my notation for the real line. Have we seen this before?
Yeah.
R. So that's the whole real line. So R notation. R is the interval minus infinity to infinity. That's a bar right in front of an R. Yeah, that's the whole real line. Every polynomial is continuous in R. We have intuitively known this. The proof of this is beyond the scope of the class. Every math major should know the proof of this, but that would take forever to prove that. But that makes sense intuitively. Every polynomial we've drawn, there have been no breaks or jumps or anything like that. What does that mean? That means that, so if I call this P, right, P of x, what does that mean about the limit as x goes to a of P of x? What is it?
It equals L. P of x.
It's P of a. Right, that is excellent work. That's the definition we gave last time about what continuity means. So again, what I love about mathematics, of course, is that the way that it's been constructed is that we just keep building upon what we talked about last time, right? So because every polynomial is continuous, the limit as x goes to a, well, first of all, P of a needs to be defined. The limit as x goes to a of p of x has to exist, and the value at a, p of a, has to be the same as the limit. And we can encapsulate all three of those things by simply writing this one line. Right? What does that mean about this? This is 5 times 3 plus 1. That means that for every polynomial, you can just simply just plug in the number, right? Which is what was alluded to on the first day of class. Someone just wanted to plug in the number, and I said, well, hold up, that's not by definition. That's true now by this theorem, right? That you can just go ahead, for polynomials, you can go ahead and plug in the number, and what happens is, for every continuous function, you can just go ahead and plug in the number. And so we'll be plugging in numbers a lot, except for certain instances. There was a question somewhere. Oh, okay, so my question on the exam about continuity and about evaluating limits will be pretty straightforward. I would imagine it would be just a few parts, and the first few, this is true of the homework as well, is that you are just plugging in the number t to the third minus 7t, the limit as t tends to 5 of 4t squared minus 6t plus 1 all over t plus 3, the limit as t tends to 0 of the sine of 3t plus 7 the cosine of t. Do those super quick. So all the functions that we've been working with in pre-calculus are all continuous on their domain, basically, right? So again, there are some functions that we use to model waves. What are those functions called? That's right. Wow, I haven't heard that term in a while. Trig functions. Other people call them trig functions, but sinusoidal is great. So if they're going to model waves, they better not have any jumps or breaks in them, right? All trig functions are continuous on their domain. All rational functions are continuous wherever the denominator is not 0. A rational function is the ratio of two polynomials, so I'm not taking the ratio of anything funky. So if every polynomial is continuous, when I divide them, that should be continuous as long as we're not dividing by 0. So what we're doing is we're setting up a finding limits. It'll only be a problem when we are going to be dividing by 0. Right? And it's not really when we're dividing by 0, it's when we get 0 over 0. Right? So this here is 6. Yes? 3 to the third minus 7 times 3, 6. This one, what funky number is this? 100 minus 30. Is that 71?
Yeah.
Over 8? Perfect. 7. Question. All of those things are nice and continuous. Just plug in the number. Yeah.
So I was doing homework yesterday, and I saw we have a limit as x approaches a of just the number of 5.
Yeah.
So I didn't know either of those. I just want to clarify. I wasn't sure that that's
5. I don't even remember that problem. I got to talk to Jessica.
Exactly
Okay. Now let's do it. Thank you. No, holding me accountable. I love questions. Oh my God. The limit as t goes to 150 of 11 equals.
11.
Oh, what was your question?
No, I was going to ask us.
Okay, no, that's right. That's exactly correct, right? So the question is, here's the function, right? The function is f of x equals 11, right? And of course, we want to ask, well, what does 11 get closer and closer to as x goes to 150? But f is always 11, right? So it stays 11. It doesn't go anywhere. Yes.
So for the sine, cosine, limit questions,
Yeah.
is it just the number that's on the outside?
Say that again?
Is it just the number?
Oh, no, so this is equal to, thank you for the clarification. This is equal to, because trig functions are continuous, the sine of 3 times 0 plus 7 times the cosine of 0. I'm plugging in the number. The cosine, this is equal to 3, the sine of 0 plus 7 the cosine of 0. What's the sign of 0?
0.
What's the sign of 0?
0.
0. Why is that? Why is the sign of 0, 0? It's the what?
The x-axis.
What's the x-axis?
There's no degree of rotation, so there's no.
Right, so you're invoking the I am going to love your particular development to start talking in sentences mathematically. It's going to be great. That's good. You see, everything you're saying is right, but then it's not fully developed, right? So 0 degrees, these functions are all in radians, okay, not degrees. So 0 radians is here, and what's the radius of the circle? 1, and therefore this coordinate is
0.
0, 1, and the sign is the
Opposite of the components.
okay. This is good. Now, what coordinate is this, by the way?
1.
Thank you. It's 1, 0, right? And the sign is the what?
Y.
The sign is the y coordinate. The sign is the y coordinate, and so the sign of 0 is 0. The cosine of 0, therefore, is 1, and 7 times that is 7. Okay. So this often happens, that some sort of shakiness with trig, you need to fix it. That's the college professor in me, right? So this is what happens in college. You're going to get into a college class. There are two things. You're going to get into a college class, and then particularly at the schools that you all were telling me about, that there will be no patience for not knowing pre-calculus before calculus. Like, there's just none of it. That she will not give a damn, right? Dr. Whoever, if you don't know pre-calculus, that is your problem, right? So we operate, again, we're just crazy. We operate like this is the only class you ever take. I don't care how many other credits you have. I don't care what's going on in physics 2, chemistry. This is the only place in the universe, and you better know everything before this class 100%. And I'm not going to spend any time talking about it, right? I mean, that's the default at Princeton, MIT, this place, right? It just so happens that I'm here this summer, right? And I'm fueled as a teacher over the years. But yeah, just if you find gaps in stuff, you better get on it, right? Because again, if you write that this is 1, then you have to rely on the grader to hopefully give you some partial credit and all of that nonsense, right? But again, that's the biggest crime. The biggest crime is when you know how to do this and then you're messing up on stuff that's beforehand, right? So you have to take your education by your own hands and learn the stuff that you may not know is tight. And one of those things for sure is pre-calc. We cannot be talking about what the sign of 0 is, right? So work on that. So, and I know that in 115, you're right, in 115 they are talking about, they're starting at pre-calculus, right? And they're doing stuff there, but yeah, we can't do that. Okay, questions about this? The other ones? Was that the last one? That was the last one. Okay, great. Let's get difficult. The limit as t tends to 1 of t squared minus 1 over t minus 1. I'm going to show that that's 2. X squared minus 1 over x minus 1 we're going to 1. Looks like it's 2. Roughly. Right? At 1, it's undefined. Clearly can't plug in 1 there, right? But we don't care about what happens at 1. We care about what happens when you're close to 1, right? So as you get closer and closer to 1, it looks like it's going to 2, at least from the left. And from the right, it looks like it's 2 as well, right? We're going to show that this is 2. Yes?
Why do you think when you do like the word puzzle and algebra, like do it algebraically, why do you get the same answer?
Oh, well, that's a great question. So, of course, my first response is, what is L'Hopital's rule? That's the first response. But assuming that we know what that is, that the limit should be one thing. Right? So all we're saying is that there are multiple ways of doing this, right? And so I'll allude to L'Hopital's rule in just a second. But the first thing we'll do is we'll plug in the 1, right? So the first thing we should do is let's see what happens. Plug in 1. We know that that's problematic. If you plug in 1, we get 1 squared minus 1 over 1 minus 1. That's 0 over 0. Okay. And so that could be anything. And so this requires that at this point we use some algebra. And for the next few problems, this is the condition that we will be dealing with. What happens when you get 0 over 0? Because this will lead directly into being able to calculate derivatives by the definition. Okay. So now you are alluding to the fact that this is a fight, right? The question is, I know this is going to 0, right? Yes? I know that this is going to 0. Now, what else do I know? I know that if this was going to 0 super fast, faster than this was going to 0, what would the answer be? It would be 0, right? If this flies to 0 faster than this gets to 0, the whole thing would be 0. If this went to 0 way faster than this, what would the answer be then, dividing by 0? It would be undefined, right? It might be some infinity or something like this. Notice what I said. What word did I just use? Begins with an F. Faster. I said faster, right? So that if the rate of change was higher for the numerator to 0, then the answer would be 0. If the rate of change for the denominator was higher, then the answer would be something else, right? If the rate of change for each one was the same, then I might get an answer. In this case, it's 2, right? So that asking about a limit that involves 0 over 0 can be reduced to talking about the derivatives of those things. Right? And so later on we'll prove that to answer this question, I just need to look at the derivative of t squared minus 1 and the derivative of t minus 1. That how fast they go to 0 is the real question. Right? And of course, that would be true if it was infinity over infinity. Right? When you have that fight, you're asking, how fast is this one going to infinity? That's a question about the derivative. And that's why in L'Hopital's rule, you can use the derivative to do that. Right? Is that okay? That makes sense? That's why we're using it. So L'Hopital's rule will work here, right? But it is using an atom bomb to kill an ant. Right? You don't need to use that. I have so much to prove before I prove L'Hopital's rule. I have to prove the mean value theorem. So there are all sorts of things there. Okay, so the algebra is trivial. We just need the factor, right? The limit. Oh my goodness. Here we go. This is greater wingers here. The limit is t tends to 1 of t squared minus 1 over t minus 1 is equal to what?
The limit.
Whew, that's right. That's all I needed to hear. Of what?
T minus 1
times t plus 1 over t minus 1. And then this is equal to the limit as t tends to 1 of t plus 1. These cancel, right?
Yeah.
Now I can't cancel 0. How do I know that t is not 1? How do I? Because t is getting close to 1, but not equal to 1. So as long as t is not 1, I'm free to cancel that. This now is 2 because t plus 1 is a polynomial, and I can just plug in the 1. So we'll spend the next few problems talking about all this crazy algebra for all sorts of problems you might run into in order to solve these types of problems. I'll take any questions about this. So I'll give you a function, ask about a limit, go into a number, plug in the number. If you get a number, that's the answer. Right? If you plug in a number and you get a number and it's a fraction and you get a number up top that's not 0, you get a 0 in the denominator, the answer is undefined, or the limit does not exist. If you get 0 over 0, you should try to simplify. I'll open the floor to questions about that. On the homework, we did something like this. The limit as x goes to 9 of the square root of x minus 3 over x minus 3. For a mathematician, this problem is, 9. This problem is not that different. I talked with Jessica about this. I'm going to do this in 2 ways. She wanted to do this in one particular way. I was like, there's no way anyone does it this way. So I'm going to see if people see this the other way. I usually use the conjugate to simplify. First of all, you plug in the 9. I had already primed you that for the rest of these, you'll get 0 over 0, but you do want to go through that step. If you plug in the 9, right, it's the square root of 9 minus 3 over 9 minus 9. That is 0 over 0. And so we'll simplify the limit as x tends to 9 of the square root of x minus 3 over x minus 9 is equal to the limit as x tends to 9 of the square root of x minus 3 over x minus 9. And then I'm going to introduce the square root of x plus 3 over the square root of x plus 3. So a little bit of math magic. This thing is called the conjugate. And it's the conjugate of the square root of x minus 3. So this term comes from complex analysis, where we have a plus bi, 2 plus 3i. The conjugate of 2 plus 3i is 2 minus 3i, right? So you just change the signs. Why am I doing this? I'm doing this because when you plug in the 9, you get 0 over 0. This means that x minus 9 is a problem. And so we just get committed to trying to cancel it out so we can actually plug in the 9. Like, we're trying to get rid of this 0 over 0 issue. And by introducing this, you get that. You resolve that issue. This is equal to what?
X squared.
No.
X minus 9.
No.
The
The limit as x tends to 9. I'm going to get some people. I don't want to. But yeah, so you are going to have me take off points. And so it's this thing. Again, I know some people are going to skip this step, of course. That's okay. All right, so this is equal to the limit as x tends to 9 of, and then we need to FOIL this. Right, so
X minus 9.
x minus 9 all over x minus 9 times the square root of x plus 3. Right, so again, it's when you find my cursor again. Where'd you go? There you go. So it's the square root of x times the square root of x is x. So it's just a minus b times a plus b, right? And so it's a squared minus b squared, and that gives you x minus 9. And then the x minus 9's cancel. It's the limit as x tends to 9 of 1 over the square root of x plus 3, which is 1 over 6. My sister Jessica then says, oh, well, no, I would have never done it that way. I would have factored x minus 9. Yeah, I know, you could. I could. I said, no, who's going to factor x minus 9? But I guess we got some people doing that,
Oh, yeah,
right?
I guess that's it.
Say it again.
So I guess that makes sense.
No, of course you could do it,
You could visit the more complicated way.
right? So or right, the limit as x tends to. So she's been vindicated. Okay. Square root of x minus 3 over x minus 9. I can't even do this. This is crazy, right? The limit is x goes to 9, and then x minus 9 is the square root of x minus 3 times the square root of x plus 3. So you could just know that, right? Okay, so, and then they cancel, and then it's over. So I prefer to introduce the conjugate. And there's one on the homework where you have to use the conjugate, right? There's no factoring. Yeah, so, yeah. Right, so there's one way where you get a 0 over 0, and you have to introduce some new thing to do it. I'll take questions about this method. And you'll see all the other ways in the homework. Please, go ahead.
So for the very beginning, like on the homework and test, do you want us to write out that first step when you plug it in and show that it equals 0?
Oh, no, you don't have to. No, you don't have to. You don't have to do the 0 over 0. You can just get right to the work if you like. Yeah, right to step number 2. Yeah. Thank you for your question. Other questions about that? Okay. Yes, please. Go ahead.
Which way we do it?
Oh no, of course not. I mean, that's crazy. I mean, that's like a fascist type. That's crazy. Like, you must do it my way or else. Like, that's insane. Go ahead.
Just kind of like piggybacking off her question. If we know how to use L'Hopital, could we use it?
That's a great question too. The answer to that is no. I mean, because that's so it's funny you say that question is related to hers. Because I don't see them as related, right? So L'Hopital's. So this is good. So when you say L'Hopital's rule, so L'Hopital's rule means something different for us, I think, for me than it does for you, right? So for you, what is it? What is L'Hopital's rule for you? Apply the limit. Yeah. Okay. And so for me, it's a theorem that says that if you have this, then you can do this, right? And at this point, I don't even know. I mean, that needs to be substantiated. We need to show that that's true, right, in this process, right? And so until we get to the place where we can demonstrate that that's a fact, then we can use it then, right? Of course, the response to that is, well, we already know it's true. We were told it was true. And oh my goodness, that's so anti-student. Right? That's so anti-intelligent, right? If we got a lot of adults running around this place that just do stuff that they're told. And I wish that people were like, well, hold on, wait, why is that? Why is that? Right? So, I mean, and if you want to just do whatever I tell you, I got some, you know what I'm going to say? I got some beachfront property in Iowa that I need to sell you, right? For real cheap. So, yeah, we should always be questioning why stuff is true. Right. So we'll get the L'Hopital's rule and we'll use it, right? So, and I get that means like you already know how to do it, right? But again, we're trying to go deeper with concepts. But that's a good question. Other questions about this? Okay. All right. I think we're ready to introduce the derivative. We got to remember why we're here. Right? I was on that toll road speeding along, and she put the radar on me, right? And found out my speed at an instant. And even worse than that, take her out of the equation. She was all the way at the end of the toll road and said that I was speeding at some particular moment. She used the mean value theorem, whatever that means, right? And so, again, we want to know how fast we're moving at 3. And it was true that, again, we can find out how fast the average rate of change from here to here is just the slope, right? But That's not what we're interested in. How fast are we changing directly at 3? At 3. What's the slope there? And as you might expect, what we're going to do is we are going to find, that's really good. We're going to find that slope, and then this slope, that slope, that slope, right? So we're just going to keep finding slopes closer and closer, right? So another way to do it is to just get rid of all of these and do this, right? So I'm going to get rid of this one too. So, and that one. So I want to just find the slope between here and here, not there. The slope between here and there. Oh, that's bad. And then what do I want to do? Of course, I want to bring this point closer and closer and closer. That's what I want to do, right? So along this graph, I can get approximations to the real slope at that point. And oh my goodness, if that doesn't look like a limit, I guess I've just done a terrible job, right? Then I want to take the limit of this slope as this point gets closer and closer to the point I'm interested in. And as you can see, that I don't care about what happens at the point, because at the point you get nothing. You get 0 over 0. This is why the notion of limit is supremely important, right? That when we talk about limits, we don't care about what happens at the point, but what's happening to this slope as you get closer and closer. And what's nice about GeoGebra is that it gives you the line. It doesn't give it to us in the nice form, right? It doesn't give it to us in y equals mx plus b form so that we can see immediately what the slope is. If it did that, then we would be able to know what the derivative is automatically, because the derivative is the slope of this curve, right? But it's okay, right? So they can give us everything, right? So that's what we're doing, right? And that's why we have to talk about limits. That's why we have to talk about limits and continuity. Of course, if this point was never there, I would have never asked about the derivative, and that's why we need to talk about continuity. Okay. Let's get to it. Let f be a function. I might give two formulations of this. The derivative of f at x equals a is, for sure, it's a limit. I want to go here. So what we're doing again is that we are taking a limit of these what? Of these slopes, right? It's the limit of all these slopes. And so here, now I'm going to go ahead and copy this. Right, so here, this is like, this is going to be A, right? Or I should actually call this, I could call this X, right? So I can call that X. And now there's some point T here, right? And then what am I going to do with T? What's going to happen to T? I'm going to move T towards X, right? And then I want to look at these slopes. I want to look at what happens to these slopes. And so what is this value here? What is that y coordinate? No, in general, for any function, what is that y coordinate? At t, it's f of t. Questions on that? This y coordinate is f of x. And I care about the slopes. Where are the slopes going? What's the slope of this line?
F of t minus
F of t minus f of x all over
T
minus x, and I want to take the limit as t goes to x. Question? Whatever that is, I'm going to call that the derivative. Whatever that is, and that's the definition. I think I called it a just now.
Yeah.
I'm going to change that to x.
So you want to keep it T and X?
Yeah, I'm going to make it t and x, yeah. At x is given by the limit as t tends to x of f of t minus f of x all over t minus x. Oh, I feel it already. Some people are like, wait, that's not what I was told before in my class, right? They use H's and all that other stuff. Oh, yes, I see. I'm a mind reader, player. Of course, I have to rectify my definition with the definition you may have seen earlier, and I'm going to use them interchangeably. If I want to show that the derivative of sine is cosine, I'm going to use some H's. I could use this one. If I want to show that the derivative of x squared is 2x, I'm going to use this one. Right? So if all the definitions are the same, I should be able to use each one interchangeably at the same thing. All right, so yeah, that's it. That's the derivative of it. Here's the notation. I'm going to call that this. T is, give me one moment. T is going to x, and so whatever I get at the end obviously depends on what letter. At the end, what should be the only letter left? X, right? So this is a statement about both t and x, but then t is going to x. All the t's have to become x's, and so whatever's left is a function of x. So this is going to be some function of x, and we call it, in this way, we call it f prime. Please.
So do you also use the dx form for the derivative?
I do. That's due to Leibniz. So if y is f of x, then we can say that this is dy. This is dy d. Well, f was a function of t, so this is like dy dt at x, right? So, but yeah, usually we use dx, dy dx. If y is a function of x, yeah. Please.
So the derivative of f at x is the limit of the rate of change in those are tangential lines.
We call them secant lines.
Secant.
Yes, it's the limit of the secant lines. Yes, as one of the endpoints goes to x. That's right. That's exactly correct. Any questions about this? Good, good. The other formulation, of course, I'll go back. I think that's just this page, right? And then I'll get out the eraser and say, no. Here's x. And I'm just a little bit farther away. Just about a little bit. If it is the case that t was going to x, that means that t is just x. And by the way, I'm so biased. I'm always coming from the right. I can make this entire argument on the left, right? So it doesn't matter whether you're coming from the right or the left. So here, instead of putting t, I could say x plus a little bit. And the number is going to x after all, so the number has to be close to x. So it's just x plus a little bit h, where h is small, right? And of course, you know what I'm going to do with the word small. Small. Right? So then, what is this y value? F of x plus h. This is f of x. The slope is therefore f of x plus h minus f of x all over x plus h minus x. Absolutely right, which is f of x plus h minus f of x all over h. And the intention is that if I want x plus h to go to x, that really means I need h to go to 0. So that, I'm sorry?
Why 0?
Say it again?
Why 0?
Why is it? That's a great question. My intention, this was t, right? Thank you for your question. My intention was that I need to move this towards x.
X.
That means that this thing needs to go away, which means that h needs to go to 0. Excellent. Good. Good. All right. What does that mean? That means, or it's the limit as h tends to 0 of f of x plus h minus f of x all over h. Yeah.
You might have said this earlier, I remember, but did you say you're going to might use either of the definitions?
Oh, sure. When I want to show that the derivative of x squared is 2x, I'm probably going to use this one. When I want to show that the derivative of sine is cosine, I'm going to use this one, right? So that's why I'm using both of them. Yeah. First question on the test is define the derivative of f at x. So write both, either one or both. This is fine. And then I'll ask for a couple of interpretations. We've been good at that so far. So, interpretations, let's add a page. Interpretations. I'll ask for 2. The derivative of f at x equals, or I should just say it x. What is it?
Limit.
No, in words, what's the street version? Interpretations are what would you tell somebody? What's the derivative of f at x? It's the slope of the line tangent to the curve of f at x. And 2, it's the rate of change. I need a word in front of that. Right, so it's the instantaneous rate of change. Instantaneous rate of change of f at x. Perfect. Okay. Questions about that? Yes.
So both interpretations they're saying the same thing.
They are saying the same thing. That's right. So this is a graphical interpretation, and this is just a functional interpretation. Right? So, and you'll see both will come up a lot, right? So that we'll be asking about the slope of the tangent line forever and ever and ever. And this makes sense because the derivative, if a function has a derivative, then it looks linear. And so we can ask about that line. And then this will be asking how fast things are moving. So questions about velocity, right? Questions about marginal revenue, right? Are all questions about the derivative. And this is precisely why, math is just the greatest thing ever, because in chemistry and econ and psychology and physics, everywhere, right, we're always asking about how fast something's changing. So the derivative shows up in tons of places. Okay, great. So now let's go back to x squared minus 3. You think I forgot? We had x squared minus 3 at x equals 1, and I said, well, what's the derivative at 1? And someone said, oh, it's 2. Right? We're going to show that in just a moment. And then we're going to find the equation of the tangent line at 1. We did this on the first day of class. You were so nice in taking us at our word that the derivative is 1. I'm sorry, the derivative at 1 was 2. So let's go ahead and demonstrate this. So find, oh, I'm sorry, I have to say this for some of you all. Use the definition. Use the definition to find f prime of 1. So what I mean by that is the derivative at 1. We'll do this both ways. We'll use both definitions. I know that some people prefer one definition over the other. And that will also happen, that your professor will do things one way and you want to do them another way. Just make sure that's okay with her. The limit, so f prime of 1. So we can do this in a couple of ways. We can do what f prime of 1 is, or we can find f prime of x and then plug in 1. Please, go ahead.
When we write the instantaneous rate of change, we just write IROC, or like would you rather us?
As long as we define IROC. So you have a definition. What is IROC? Instantaneous rate of change. I accept that. Okay, so you can write IROC. Wow, I've never heard that before. This is great. Okay. All right, so I want to do this first so that we just get this. So recall that f prime of x is equal to the limit as t tends to x of f of t minus f of x all over t minus x. Right? And this is simply what we want to calculate. You'll get super quick at doing these, right? And so we'll just break this down here. 1, we need to find f of t. 2, we'll find f of x. 3, we'll do f of t minus f of x. And listen, it is going to be the case that that you're going to get 0 over 0 every time, right? And you're going to have to always do algebra to do this problem, right? This is why we talked about limits, right? And so, and then you're going to simplify that, and then you're going to take the limit. I get that this may be breaking it down too much. I don't even know if that's possible. We'll do those 4 things, okay? And then we'll plug in the 1. Now, we can plug in the 1 immediately if you want. So we want to know f prime of 1. So f prime of 1, we'll plug in the 1 immediately. Is the limit as t tends to 1 of f of t minus f of 1 all over t minus 1. That's what we want to find. Okay. And so for these steps, we're going to find f of 1. I'm sorry, that's f of t. They're going to find f of 1, f of t minus 1, 1, 1, and 1. And then this is a 1. We'll do x in just a second. All right, f of t, what's f of t? F of x is x squared minus 3. F of t? T squared minus 3. Perfect. F of 1?
Negative
1 squared minus 3 is equal to negative 2. Okay. 3 f of t minus f of 1 all over t minus 1 is equal to t squared minus 3 minus negative 2 all over t minus 1 is equal to t squared minus 1 all over t minus 1. And oh my goodness, we need the limit as t tends to 1 of t squared minus 1 over t minus 1. And I hope that looks familiar. So this was the first limit problem we did. You plug in the 1, you get 0 over 0, but we already knew that was going to happen. This is equal to the limit as t tends to 1 of t minus 1 times t plus 1 all over t minus 1, which is equal to the limit as t tends to 1 of t plus 1. And it's the number 2 that we said before. Please.
I have a question. You add at the very end, you add the limit as actually like cancel out the t minus when you say limit. The limit as t tends to 1 of t plus 1.
Yeah.
Should you add that stuff, or can you just go straight to the answer instead of having the
You just want to write 2?
No, as in like I write limit as t tends to 1 t minus 1 times t plus 1 over t minus 1.
Yeah.
So I have cancel.
Oh.
And then I go straight to the answer.
Oh no, that's fine. I'm just not a big crossing out person. Only because when you're taking notes, taking good notes means that when you go back and look at stuff, then you can understand what you did. And crossing out makes your notes look really bad. I mean, if you just have a bunch of crossing out stuff. Now that's an opinion, of course, but I don't cross them out. Okay. Okay. So the other way, if you want to use the other definition, then we're talking about f prime of 1. Or f prime of 1 is equal to the limit as h tends to 0 of f of 1 plus h minus f of 1 all over h. I'm going to make sure I wrote the other definition the way I want it. Let me go back here. Is it here? Yeah. Okay, great. All right, so not any different. We need f of 1 plus h. We need f of 1. We're going to subtract, divide by h, and then take the limit. We need f of 1 plus h minus f of 1 all over h. And then we need to apply the limit. Limit as h tends to 0. So the steps are analogous. This way is a little bit more tedious. We'll recall that f of x is x squared minus 3. And therefore f of 1 plus h is 1 plus h squared minus 3. Which is equal to, we'll simplify now, it's 1 plus 2h plus h squared minus 3. Oh, please.
So, with the 1 plus h and the t you did earlier, can you do the f of t? You always plug in the t into the original.
That's correct. That's right. That's right. Thank you for your question. H squared plus 2h minus 2, right? That's f of 1 plus h. F of 1 never changed. Is that negative 2?
Yeah.
Yeah. Step 1, step 2, step 3 is then subtract those two things and divide by h. F of 1 plus h minus f of 1 all over h is equal to h squared plus 2h minus 2 minus negative 2 all over h. That's equal to h squared plus 2h all over h. Everything has an h in common. This is just h plus 2. And then we apply the limit. The limit as h tends to 0 of h plus 2 is 2. Questions there? So pick one. That's the definition. We talked about the great skeptic, someone who comes in fundamental to progress in mathematics. Before the great skeptic came in and said, well, wait, what does small mean? Wait, what does close mean? Wait, how do you prove that? Wait, are you sure about that? Wait. Show me. The great skeptic revolutionized mathematics. Okay. In the same way, so does the overbearing student. The overbearing student comes in and he says, that was great. What would you do when x was 3? We're at office hours. And I say, oh, okay, well, if x is 3, then I need to find f of 3 plus h. And then I do 3 plus h squared minus 3. I find f of 3. I subtract, divide by h, take the limit. I end up getting what at 3? What is it at 3? What's the derivative at 3? 6. I end up getting 6. Right, so I go through this process and I end up getting 6. Right, so let's see how that happened. Right, so that would be a 3, right? That would be a 3. Right, so what would happen? 2 times 3. Right, and then there's going to be a 9, right? And then what's this going to be? I'm sorry, so this is going to be a 9, a 3. Things are going to subtract. You're going to get 6 for sure, right? Then he says, oh, what happens at 5? And then I go back here and I say, oh, I put the 5 in, go through that whole process, I get 10. And then he says, oh, what happens at 11? I go through this whole process and I get 22. And then he says, well, wait. I said, hold up, let's stop there. We're on a deeper level than this. It sounds like every time you give me a number, then I come up with another number. There's a name for that. You give me one number, I give you one and only one number back. That's a function. That sounds like a function. And so what I probably want to do with this wonderful student is instead of going one by one, I probably want to come up with a function. And so instead of going one by one, I then just annihilate this question and just ask, well, what in general is the limit as h tends to 0 of f of what plus h? What is it? X. So that no matter what he asks me, I can just answer the question. And then I get a formula for it. And then when he says, well, what happens at 4? What happens at 7? What happens at negative 423.72489? I say, oh, just plug it in that formula. Right? Just plug it in that formula. And so when we're looking at x squared minus 3, it looks like when he gave me 4, you got 8. When he gave me 12, you got 24. When he gave me 10, you get 20. Sounds like it's 2x, doesn't it? Sounds like the derivative of x squared minus 3 is 2x. Okay. Let's just go ahead and show that that's the case. Okay, please.
Before the last page.
Yeah. This might just be up. Yeah, go ahead.
Do you still do the limit as h equals to 0 for that third step, or do you leave it up to the last?
Well, no, this is a great question. So I had broken it down into these steps, and so some people just like to roll the whole way, and I have no problem with that. Some people just like to write it all in one line and say f prime of 1 is the limit as h tends to 0 of f of 1 plus h minus f of 1 all over h, which is equal to the limit as h tends to, 0 and then they do 1 plus h squared minus 3 minus 2 all over h, which is equal to, and they just write it as one line all the way until you get to 2. And if you want to do that, that's great. Just be right. Right. So, but particularly for people that have not seen it before, I just say, do this, do this, do this, do this, right? And so again, that's a pedagogical thing, right? So I'll be in math phase sometimes I'll be in teacher phase. That whole 4-step thing is full teacher phase. It's like, if you want to know how to do these problems, you just do this, this, and this, right? Is that okay? Yeah, go ahead.
Could you scroll up?
Oh, thank you.
First,
Here?
before.
Before. Yes.
Yeah.
Yes, go ahead. Somebody favors this one. Someone likes this way better. Okay. So the derivative of x squared minus 3, we're thinking it's 2x. I'm going to deal with this 3 first. If there's any justice in the world, what should the derivative of 3 be? Because when I say f of x is 3, that means that for every x you get 3. How much is f changing? None, right? So we'll do that first. Actually, go ahead. Prove that the derivative of 3 is 0. Prove that the derivative of 3 is equal to 0. And then we'll prove that the derivative of x squared minus 3 is 2x. And then we'll end. That'll be good. Brother, do you have this?
Yeah.
Okay, good. Yeah. The limit, if f of x equals 3, then f prime of x is 0. That's the claim. What is f prime of x? Here's the proof. F prime of x is what? Oh, that's what we were trying to prove. What do we know f prime of x is equal to? What is it? What is f prime of x?
Instantaneous change.
Yeah. But now I want to actually do something. What is it? No. It's the limit. Oh, I know. Getting on your nerves already. I know. It's the limit as t goes to x of f of t minus f of x all over t minus x. I love these moments where someone's just like, can't we just know it? Right? This is what we know, right? That's the definition. What's f of t? 3. F of x? 3. This is equal to the limit as t tends to x of 3 minus 3 over t minus x, which is equal to the limit as t goes to x of 0 over t minus x, which certainly is 0. That's the proof. So again, what we're doing is we're unwinding all of this programming, right, and filling it in with all these reasons why, right? So again, we had the intuition for this. We knew that any function that doesn't change, if the derivative intuitively measures how much something changes, or it measures the slope of this horizontal line for sure would be 0. Please.
So the derivative of prime of 3 is 0.
This is good. So if the function is always 3, then its derivative is always 0. Right. So the way that you would say this, if f of x is equal to 3, then f prime of x is 0.
Oh, so you got like 1 straight line.
Yes. Then we're saying the slope is 0 the whole time. Newsflash, right? Right? That's not so surprising. I do this. This is purely pedagogical. I do this teaching-wise because it gets us used to using the definition. And it also gives us some validity that mathematicians just don't roll around saying, yo, this is like this is like this. You get this in those other classes, right? But everything that we ever say in a math class has a proof, right? So, and again, that's the beauty of it, right? I'm only preaching to this choir right here, the future math major. But yeah, but everything can be justified. So you can always say, yo, Winger, why is that true? I need the proof of that. And either I would say, okay, here's the proof, or I would say that would take forever. Here's where you can find the proof, right? And so now let's deal with x squared. I want to know the derivative of x squared. We're claiming that it's 2x. The derivative of x squared is 2x. Okay. That's a claim. And so this has far-reaching implications. This means that I don't have to, if I know about x, I know how x squared changes everywhere on the real line, right? So that when I ask about the derivative of x squared, what's the derivative of x squared at -1? What is it?
2x.
No, at -1.
-2.
It's -2. Is f increasing or decreasing at -1? It's decreasing. We automatically know that about the function, right? Now you can imagine we're going to, from pre-calculus, all those functions you learned in pre-calculus, all those functions that we tried to remember the graphs of, right, but we don't, right? Whatever arctangent is, arctangent minus 3x plus 5. I have no idea what the hell that thing looks like. But I know one thing. I'm going to be able to take the derivative, plug in a number, and I'll know whether it's increasing or decreasing there. Right? How amazing is that? That without even knowing what the graph looks like, the derivative is going to tell us whether it's moving up or down. Right? That's what's really nice about this. So I don't need to know anything about x squared in terms of how it looks to know whether it's increasing or decreasing. Right? That's pretty nice. Okay, so show that the derivative of x squared is 2x. Well, I'm going to call f of x squared. I believe we are going to be ending with this. F of x is x squared. F prime of x is equal to the limit as t tends to x of f of t minus f of x all over t minus x. So what this is going to require us to do is do some symbolic stuff, but that's okay. The limit is t tends to x. What do I mean by symbolic stuff? It means that we're going to factor just like we factored with that 1, but we're going to use x instead. What's f of t?
T squared.
T squared. So I'm going to do this in one line. Where's that cursor again? There you are. T squared minus x squared all over t minus x. Perfect. This is equal to what?
The limit.
The limit
T
tends to x of
t minus
x times t plus x. Excellent.
Over t minus x.
All over t minus x. Is equal to
the limit as t tends to x.
As t tends to x of t plus x. And all the t's become x's. This is
2x.
X plus x, which is 2x. Please.
So you said there's 2 assignments due Sunday, or is it just 1 assignment?
So the assignment that was on derivatives that was due Sunday has been moved to Tuesday. Yeah. So one of the things you have to do in the homework portal on myopenmath.com is just keep checking due dates.
Okay.
You should go in every day anyway.
Yeah.
But yeah, so again, what I don't want to do is have due dates set and it's not in line with what I feel is an appropriate pace for the course, right? I did not want to say that this was going to be due Tuesday, and then my course is centered around you, not around due dates. You know what I mean? So that when I found out that I was not going to get fully to talk about derivatives, then I was going to move the due date.
I just want to, because I was going to do it tonight, but I heard...
Well, it's open.
Yeah, it's open, yeah. I heard it's moved or something.
Yeah.
Thank you.
Okay, very good. Well, in there, I want you to have a great weekend. Jessica will be there on Sunday. I may drop by on Sunday as well for study time. So, yeah. please.
I just don't understand. I understand like but I don't understand why that was.
Yes, yeah, we'll have to talk about that. Good. Well, I'll answer bring that question on Monday. Okay, great.
It has to do with
Let me stop recording. Give me one moment before somebody says something they don't want to have recorded.